All right, we're going to look at graphing a complete graph of a rational function. So one thing to know is that I do want you to be able to use your graphing calculator to help you find the graph of a rational function, but a lot of graphing utilities, graphing calculators, or Desmos usually leave out some important features of rational functions. They don't always do a great job of that. So there are some key features that the graphing calculators or graphing utilities don't usually show, and those really usually have to do with the issue that rational functions often have a restricted domain, and graphing utilities often have a hard time near the domain restrictions. So that'll just be important to keep in mind. All right, so you can see these are the steps I'm going to follow as we go through the next couple of examples. So we're going to use the graphing calculator to help us, and you could certainly use that at earlier points in the work, but we're going to go ahead and do kind of everything above that by hand and use the graphing calculator to get some extra points and sketch the curve. Alright, so I'm going to scroll up so you won't be able to see this step, but always first things first, no matter what else you're doing with a function, thinking about the domain is always a good place to start. So let's start there. Alright, so with this function, as with any rational function, when I think about the domain, I'm going to focus on the denominator here, and I know that I'm going to want to avoid any values that would make the denominator equal to 0. So you might be able to just look at the denominator and think about the values of x that would make the denominator 0. This one factors, so I'm going to go ahead and factor the denominator. If it didn't factor, you could set the denominator equal to 0 and solve for x using maybe quadratic formula or synthetic division to find zeros of a polynomial or whatever. Okay, but on this one, once I've factored it, it's pretty easy to see that you want to avoid x equals -4 and x equals -1. Those would be the values that make the denominator 0. So I want to avoid those values. So when I state what the domain is, it would be all real numbers except -4 and -1. So I'm going to write that in interval notation. -infinity to -4, then -4 to -1, and -1 to infinity. Okay, so because the domain is in 3 pieces here, that tells me that when I graph my function, I'm going to have 3 pieces to the graph. So 3 different pieces to look for, and when I look on my graphing calculator or Desmos or whatever I use to help me with the graph, I need to make sure that my window is showing 3 different pieces of the graph on each of those x intervals. All right, the other thing is that when you have breaks in the domain, that is where you're going to have discontinuities in the graph of the function. And so you want to think about whether those discontinuities are holes or vertical asymptotes. For rational functions, those are the 2 kinds of discontinuities you're going to have. And so the holes occur when you have a factor that cancels, and in the simplified version of the function, you wouldn't have that factor anymore. But I don't have that here. The denominator has factors of x plus 4 and x plus 1, and the numerator does not have a factor of x plus 4, x plus 1. So for this one, both x equals -4 and x equals -1 are vertical asymptotes. So I'm going to go ahead and put those on the graph. So we're going to put a dashed vertical line at x equals -1. So that would be all the points that have an x coordinate of -1. That's this location here, and x equals -4. Okay, in the order in which you do these steps that I listed out at the top here doesn't really matter. So you could find other things before you found the discontinuities, but I always start with the domain, and then the domain directly tells you the discontinuities. So since I have a couple of asymptotes already on the graph here, I usually go ahead and find asymptotes next. So horizontal asymptotes. And there's a lot of different ways to think about horizontal asymptotes. So the way we talked about in class, though, is thinking about what happens when x gets large, what happens to the f of x function. So really this is when x approaches either positive or negative infinity, what happens to the f of x function. And so it's going to be dominated by that 3x term on the numerator and the x squared term on the denominator. And when I reduce that, I get 3 over x, and so I want to think about what happens to the value of 3 over a number when that number gets bigger and bigger and bigger. And so when I think about putting in numbers on the denominator like a million, a billion, a trillion, see that the value of that fraction is going to approach 0. So I have a horizontal asymptote at y equals 0. There are some rules that you might know about degree of numerator and degree of denominator, but the reason those rules work is really because of what we talked about right here. So some rational functions also have slant or oblique asymptotes, but a rational function won't have a horizontal asymptote and a slant asymptote, so there aren't any slant asymptotes on this one. All right, the next thing I listed on the list of steps was to find the intercepts, x and y intercepts, and so sometimes you can use a calculator to help you find those, but I'm going to go ahead and do those here by hand. So for any function, not just rational functions, when you find an x-intercept, that's where the graph crosses the x-axis, so you're putting in y equals 0 and solving for x. So from our original function, I'll put in 0 where the output is. So I'll have 0 equals 3x plus 1 over, I'm just going to write the denominator in that factored form here. It doesn't really matter which way you write it. And then I want to solve for x. So this is where your algebra skills come in. Here I have a fraction equation and I'm trying to solve for x. So I'm going to multiply both sides of this equation by the denominator. That is to get rid of the denominators on the right side. You have to remember, if you're doing that to an equation though, you have to multiply both sides of the equation by whatever you're multiplying through by. So conveniently though, when I multiply on the left side, 0 times whatever is still going to be 0. And then on the right side, when I multiply that fraction with the denominator of x plus 4 times x plus 1, multiply that times x plus 4 times x plus 1, the x plus 4 and x plus 1 cancel, and I'm just left with 3x plus 1. All right, so from there, I can pretty easily solve for x. I'll subtract 1 from both sides and divide through by 3, so that will give me x equals negative 1/3. I have an x-intercept at y equals 0, x equals negative 1/3. So I'm going to put that here on the graph, and I'm going to go ahead and label that point since it's hard to tell from the graph exactly what fraction that would be at between 0 and negative 1, so I'll go ahead and label it. All right, and then the other intercept to find would be a y-intercept, and so for any function, not just rational functions, when you're finding a y-intercept, that is when x is equal to 0. So I'm going to go ahead and plug into the function what I get when I plug in x equals 0. So I'll have 3 times 0 plus 1 over, and then I can either use the factored form or the original form. I'll just use the original form this time, 0 squared plus 5 times 0 plus 4. So you can probably think this through, that you aren't necessarily going to have to write out this step every time, because when you put in 0, then these terms involving 0 will all just be 0, and so you're just going to be left with 1 over 4. So I'm okay if you skip writing some steps out there as long as you're doing it correctly. So that point is going to have x coordinate of 0 and a y coordinate of positive 1/4. So again, that's hard to see on the graph exactly where it's at, so I'm going to go ahead and label that 0, 1/4. All right, so those are the things that I would like you to be able to find by hand: the domain, the discontinuities, asymptotes, holes, if there are any, and intercepts, x and y intercept. And then from there, I would use the graphing utility to help you get some more points. You want to get some points in each region, so the points that I have plotted here from my work are all in the region that is to the right of x equals negative 1. So maybe I use my graphing calculator, I type in the original function. When you do that, you'll want to make sure that you put in parentheses around the entire numerator and the entire denominator, or if it has what's called pretty print, where you can put the 3x plus 1 on the entire numerator and the x squared plus 5x plus 4 on the entire denominator. But if you just use a slash for the fraction bar, then you'll need to put parentheses. You should expect to see on the graph the stuff that we already figured out. It won't show the asymptotes probably, but you should be able to see breaks in the graph at negative 1 and negative 4. You should be able to see the points that we already found, 0, 1/4 and negative 1/3, 0. And then I would just use that graphing utility to find a few other points. So you might look for points that look like high or low points, or maximum and minimum values on the function. So when I graphed this on my graphing calculator, I saw that there appears to be a point right here at about x equals 1 and y equals some fraction amount, about 0.4, I think it was. So I plotted that point, and then I know that on the right side of the graph I have have a horizontal asymptote, so the function is going to get closer and closer eventually to that horizontal asymptote. I could trace and find some other points, or I can use the table and find some other points on my graphing calculator. And then for these, it'll connect these points, and then it's going to go down. You can see on your graphing calculator screen, it goes down here along this asymptote. You can also trace and find coordinates of some specific points to help you plot that. All right, in the section of the graph that is between x equals -1 and x equals -4, it looks kind of like a little bit of a lopsided U shape, and so I looked for the point that looks like the low point in that region, or the local minimum value of the function there. And so at about -2, I just traced at -2. The y coordinate was about 2.4, I think, and so I have a point here, and then I'm just sketching what I saw on my graphing utility, this sort of U-shaped graph here. So I used the calculator to help me find that point and plotted it on my paper and went ahead and drew that shape in. All right, and then depending on the window you're in, you may or might not even see the left side, but you know from the thinking about the domain at the beginning that there has to be some part of the graph over there, left of x equals -4. So if you have to adjust your window, you adjust your window. I traced on my calculator and I found a point at x equals -5, y was about -3.4, and so I put a point down here. And I know that the function is going to approach the vertical and the horizontal asymptote. And so I'm going to go over here. I also know that the only place it's going to cross the x-axis was the point I found, -1/3, 0. So on the left end of the graph here, I know that this is going to come up toward that asymptote, horizontal asymptote, because that's what horizontal asymptotes do. But it's not going to pass through that horizontal asymptote over there. Not because you can't pass through a horizontal asymptote, you can, but because I found the only x-intercept earlier in my work. The only x-intercept was at x equals -1/3, y equals 0. So it's not going to pass through y equals 0 anywhere else. All right, so try some problems like this. I'm going to do one more example, so if you want to watch another example, you can watch that.